In this investigation, we looked at function inverses. Let's consider a couple simple scenarios to review these ideas. First of all, suppose x and y vary together such that y is equal to x squared. Given any value of x, we can determine exactly one value of y just by squaring the value of x. Therefore, y is a function of x. And maybe we name this function f. So f takes as its input a value of x and outputs the value of y. And since we know how x and y are related, we can actually write a formula for this function. So f of x is actually equal to x squared. Now we might ask ourselves the following question. Given a value of y, can we determine exactly one value for x? A simple scenario here is if y is equal to 4, can we determine the value of x? Now if you set up an equation, this would be saying 4 is equal to x squared, and therefore x is equal to positive or negative 2. So if y is equal to 4, then x must be equal to negative 2, or it must be equal to positive 2. So that this actually tells us that x is not a function of y. So x is not a function of y. Because given a value of y, we can't determine exactly one value for x. So in this case, if we look back at our function f does not have an inverse. Or I should say does not have a function inverse. We can still reason about this relationship in reverse, but this inverse relationship is not a function. So by that I mean, if we're given a value of y, we can still determine like values of x, but we can't determine exactly one value for x. So we can reason in reverse, but this inverse relationship is just not a function. Let's look at one more scenario. Suppose t and d vary together, and we have the graph of this relationship. If we imagine picking any value for t, so I'll pick a t right here, but you could pick any value of t, we can use the graph and see that there's exactly one corresponding value for d. And because of this, we can say that d is a function of t. And maybe we'll call this function g. So g of t is equal to d. So let's try to go the other way. Let's try to do our thinking in reverse. If we have a value for d, I'll pick this value of d, but you can pick any one. We see that we can use the graph to determine exactly one value for t. So if we were given any value of d, we can find exactly one value of t. So in this case, t is also a function of d. And maybe we'll call this function h. So h of d is equal to t. So functions g and h, these two functions, they represent the same relationship. So we have the same relationship, but we're kind of going in reverse. So the input and output variables are reversed. These functions kind of reverse each other. Therefore, we say that h is the inverse, so inverse of g. And since we mean that h is the inverse of g, instead of writing h for the function name of this inverse, it's actually more common to write this as g superscript minus 1, or we say g inverse of d is equal to t. So instead of writing h, we're just going to use g superscript minus 1 to represent that we're talking about the inverse of g. In general, if the inverse relationship of a function is also a function, we say that the original function has a corresponding inverse function. Even if an inverse function does not exist, we can always think about a relationship in reverse. We might just get more than one value for one quantity when examining one value for the other quantity.